Okay, going over people I don't see here. I don't see Amanda. And Diksha was here for just a moment. Jaron. And James. Okay, today we're going to be reviewing, and yes, I was working with the student and didn't get this loaded up, but it won't take long because it's not very long. Reviewing for the third exam already. And so this exam is going to be over chapters 8, 9, and 10. That is, we're going to be studying momentum and center of mass. That's chapter 8. And then equilibrium, chapter 9. And then chapter 10 is rotational dynamics. So just a quick review with more problems than anything else. Come on, one more page. And there we go. So, looking at my quick review topics from chapter 8, we studied collisions primarily here, and it started with understanding what momentum is. So momentum, mass times velocity. Simple question here. Is momentum a scalar or a vector? It's a vector because it has a direction, velocity has a direction, so it has a direction. Momentum is a vector. If I have a ball that's going 5 meters per second, hits the wall and bounces back going 5 meters per second, did its momentum change? Yes, it did. By how much? Well, you'd have to know its mass. Let's say its mass is 1 kilogram to make it easy. If it was 1 kilogram and 5 meters per second that direction, and ended up 1 kilogram, 5 meters per second this direction, what's its change in momentum? Okay? She said negative 10 kilogram meters per second. What was the negative there to indicate? The direction. She could have also said, well, the change was 10 kilogram meters per second in this direction because it's final minus initial for the change. Okay.
Just to clarify on that, was that because it was changing, like it didn't matter the original direction? Or if it was originally, if we classify it as going in a negative direction, would that have been a positive change?
Right, that's correct.
Okay.
Okay, now, this condition, know when and why linear momentum is conserved. That requires you to know Newton's second law. Newton's second law says net force vector is equal to, and what we first learned was mass times acceleration vector, but now we changed it to change in P over change in T. What is P? Momentum. Okay, just making sure you're following along. Because there's not a lot of, sense. I mean, momentum doesn't have the letter P in it. And so that's one of those things where we just kind of have to learn that P means momentum because I can't see any sense on why it would mean momentum otherwise. So the net force is change in momentum over change in time. So if I solve that for change in momentum, change in momentum is the net force multiplied by the change in time. So now I can see clearly what condition or conditions would give me momentum conserved. When force net is 0. Now I'm going to expand on that just a little bit. Newton's second law is the net force acting on my object or my system of interest. So when we're doing a collision, we identify our system of interest as the two things that are hitting each other. And so when I'm doing the net force, I'm doing the net force on those two objects. Now let's suppose that Jaron and I collided. I put a force on him, he put a force on me. if my system is the system of Jaron and me combined, then I don't have to worry about the force I put on Jaron or the force Jaron put on me, because when I add those two up, what does Newton's third law tell us about those two forces? They'll be equal in opposite directions, and thus they're going to add up to 0. So when you're doing that net force, you're only looking at the external forces that are acting on your objects of interest. So instead of me and Jaron, let's suppose that it's a car hitting another car. If two cars hit each other, we don't care about the forces of one car on the other during the collision, but we do care about external forces. So external forces would be things like the force of gravity, the force normal, the force of friction. Now, in our car collision, unless it's something like that dude on the freeway in LA who got, did you guys read about that? Ejected from his car and landed on the freeway sign. They had to go dig his dead body out of the freeway sign. That's brutal. Okay, but in our normal conditions, the cars stay on the ground, and so we don't worry about the vertical part. So we only look at the forces acting in the horizontal direction, and thus we don't worry about the force of gravity or force normal, except force normal depends on force gravity, and force of friction depends on force normal. When I have two cars colliding, there should be a force of friction acting between the cars and the ground. They shouldn't just both be coasting into each other and neither one trying to avoid it. And yet, we say that during the collision, momentum is conserved. Now, if there's this force of friction acting, and that's an external force, one might say, wait, momentum can't be conserved because there's an external force, the force of friction. So how is it that we say momentum is conserved during the collision?
Except the time to be very, very small.
Yeah, very, very small time for that collision. Before the collision, when it comes skidding in, well, clearly momentum wasn't conserved. After the collision, when they go sliding away, momentum wasn't conserved. But during the collision, because the time is so short, and it was force net delta t is what the change in momentum is, we can say, even though there is a finite force of friction acting, it's really small compared to the forces involved with a car hitting another car, and the time is very short, so we'll just pretend that's approximately 0 for collisions. So in the end, you need to understand why we say momentum is conserved in collisions, because it's not a perfect statement. And then you need to say, okay, so if it is a collision, momentum is approximately conserved because of blah, 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 and then solve from there. Yes?
The change in momentum equation is also impulse, right?
Impulse, this side here is given the name impulse. I promise you I won't ask you what is the impulse. I just use change in momentum as my words. But yes, the right side is given the name impulse, the left side change in momentum. So impulse is equal to change in momentum by definition. Okay, elastic versus inelastic collision. Nothing is perfect, okay? A perfectly elastic collision doesn't truly exist. The closest you can get is a steel object bouncing off of a steel object. Has a coefficient of restitution of something like 0.97 or something. It returns 97% of the kinetic energy. But for general physics, we pretend it does, right? Because a lot of collisions are close enough. So an elastic collision is a collision in which kinetic energy is the same after the collision as it was before. That means you had nothing that was converting the energy into sound or into heating things up or into deforming things. A perfectly or completely inelastic collision is the opposite. Now, perfectly or completely inelastic does not mean that the kinetic energy went to 0. What it means is that the two objects stuck together. And so if the two objects stick together, then you have an equation that V1 final is equal to V2 final. Whereas if they're elastic, you have kinetic energy initial is equal to kinetic energy final. And remember, I went through a nice long derivation where I had 1/2 m1 v1 squared plus m. And in the end, this got us a pretty nifty equation that was just velocity 1 minus velocity, or velocity 1 initial minus velocity 1 final is equal to velocity 2 final minus velocity 2 initial. I think was the equation you get from conservation of kinetic energy. So you need to be able to work collision problems, and I will work a collision problem in just a moment. There'll only be one-dimensional collision problems. I won't give you two-dimensional collision problems. If you can do a one-dimensional collision problem, then you should be able to do a two-dimensional collision problem. It just takes a lot more work. Yeah.
Is it a two-dimensional collision where it's kind of like the billiard balls?
Yes. Remember, the only things I said about those were the special case if you have two objects that are the same mass when they collide. Either one of them is at rest, or they're going the same direction, or they're going 90 degrees from each other. And of course, if they're going the same direction, it wasn't a two-dimensional, it was a one-dimensional collision. So that's all the two-dimensional we did. So let's look at a collision problem here. I actually didn't work this out beforehand. A 3.33 gram mass or object, I missed a word, with an initial velocity of 125 meters per second east collides with elastically with 425 gram object initially traveling at 2.25 meters per second east. What are the final velocities of each object after the collision? Now let's say you're given this on the test. What's the first thing you're going to do? Okay, first step is to draw a diagram. So I'm going to draw a diagram showing object 1, object 2, V1 initial is equal to 125. And I dropped off the vector sign. I'm just going to use to the right is positive, to the left is negative, with my definition then that east is to the right. Okay, object 2 here, V2 initial is equal to 2.25 meters per second. So I have their initial velocities. Mass 2 is equal to 425 grams. Mass 1 is equal to 3.33 grams. There's my initial situation. And they're going to collide. What's it going to look like after the collision? They will not be together. Elastically, they're going to what? It's okay. They what? They'll bounce off each other. Yeah. I was quite confident she knew the difference. That's why I stuck with her in case people were wondering, so she could show this. Yes, she knew the difference. So afterward, I'm going to have mass 1 going to the left with V1 final. Mass 2 going to the right with V2 final. How did I know that mass 1 was going to bounce off to the left? Well, it could have gone really slowly chasing after the big heavy one. But my practical experience says when I shoot a BB at a bowling ball, the BB bounces back, the bowling ball hardly changes. And since I have these masses, they're so enormously different, I expect it to be something similar to that. And so I drew a picture based on my expectation. If my picture was not the correct outcome because my expectation was wrong, as long as I do my work consistent with my picture, I'll still get the right answer. Question, Austin.
Could you just explain that with Newton's third law?
Yes. You want me to explain, or are you asking is it possible?
You asked why.
Yeah. Because, and I will finish out what Austin's thinking. They have the same force between the two objects. One of them has a big mass. Acceleration is net force divided by mass. The one with the big mass has a very small acceleration. One has a small mass acceleration is going to be very big. So it's a really big acceleration for the small thing, a very small acceleration for the big thing. Okay, now I have my picture drawn out. What's the next step for solving my problem? Talk about the concept. So my concept is elastic collision. So 1, kinetic energy is conserved. 2, momentum is conserved because in this case I didn't have any frictional force, so I'll just say because force external equals 0 in east-west direction. So that's my concept. I have those, and I'm just going to have to use the two equations to solve for two unknowns. But what are my two equations? What's kinetic energy? 1/2 mv squared. And what is momentum? Okay, so I have my equations, and now I'll just go to my work. Kinetic energy conserved. So 1/2 mass 1 v1 squared, 1 initial squared, plus 1/2 mass 2 v2 initial squared equals 1/2 mass 1 v1 final squared plus 1/2 mass 2 v2 final squared. That's my equation. Now I can instantly make a quick simplification. What's the first thing I can do instantly? Get rid of the 1/2s. Those 1/2s don't need, I just multiply everything by 2, and I got rid of those. Then, remembering what we did in class, the next step I'm going to do is to combine the m1s on the left side and the m2s on the right side. So I'll have m1 times v1 initial squared minus v1 final squared equals m2 times v2 final squared minus v2 initial squared. So I moved this over here and this over here by subtraction, of course. And then the next step, which seems to be a non sequitur, is m1 times v1 initial minus v1 final times v1 initial plus, I said the signs wrong when I said this before, you guys remember doing this? Whoops, that's a 2, not a 1. Now at this point, I stop off and go to the other equation. When I did this in class, I just did the momentum equation first. I have that equation. Now, rearranging in the same fashion as was done above, I have m1 times v1 initial minus v1 final equals m2 times v2 final minus v2 initial. And this is where I see that is the left side of my momentum equation. And this is the right side of my momentum equation. So those two things that I put the blue underline are equal to each other, which means I can divide them out. And so my kinetic energy equation, if I divide out the two things that are equal to each other on either side, it just gave me the simple relation v1 initial plus v1 final equals v2 final plus v2 initial. So that's one equation. This is the other equation. Now I need to solve by combining the two equations. Because we've already used the 1/3 of the class period that I have devoted for this chapter, I won't do the actual math for the end of the problem, but at this point I would just say, okay, I know what the initials are for both of them. And so I'll take this equation and solve it for V1 final is equal to V2 final plus V2 initial minus V1 initial. And then substitute that in here and then find what V2 final is. And once I found V2 final, then I come back and get V1 final. Yes, ma'am?
For me, the math is the part that I struggle with the most because I don't have a lot of math experience.
Mm-hmm.
Would we be able to take just a little bit of time to do
After class, I can spend time with you on it.
that?
Okay. Chapter 9, equilibrium situations. So equilibrium, we had two conditions for equilibrium. Let's start with, what does equilibrium mean? I stand up, I'm not doing it probably. What does equilibrium mean? Okay, there are two conditions of equilibrium. One is that the net force is equal to 0. And the other one that the sum of the torques is equal to 0. That's a correct answer. What I was actually looking for, equilibrium, technically, that means equal forces. So equilibrium problems technically are equal forces problems. And by equal force, we mean that if we add them all up, we get 0. And Newton's second law says if the sum of the forces are 0, then the acceleration must be 0. The rotational equivalent of Newton's law says that the sum of the torques are 0, then the angular acceleration is 0. So the two things on the left here are the conditions of equilibrium. The two things on the right are things that help me to identify, am I in equilibrium or not? If I have a system that is moving at a constant velocity, then the acceleration is 0 and it's in equilibrium. If it's changing velocity, which could be changing speed or it could be changing direction, then it's not in equilibrium. Of course, I have to look at both conditions. I also have to look at the rotational aspects. So you need to be able to identify if a system is in equilibrium or not. Second thing, something that's implied by what I've written already, you need to know what torque is. You might recall torque is the twisting equivalent of force. It's the rotational equivalent of force, the force that makes things rotate. And so torque has an equation that's defined using a cross product. That is, torque, which is a vector, is equal to R cross F. That doesn't fit very well. I'm going to write down the bottom where it fits better. Torque is equal to R cross F. What does a cross mean here? It means multiply perpendicular parts. So when I'm doing a cross product, I'm only multiplying the perpendicular parts of my vectors. So I can write the magnitude of the torque is equal to R perpendicular F, or R times F perpendicular, or R times F times sine of the angle between R and F. And yes, that's sloping uphill. My bad. All of those will give me the magnitude of a torque. How do I get the direction of a torque? The right-hand rule. So now, just to make it very clear, if you come in having things written on your fingers for the right-hand rule, that would be considered cheating. Okay? Just in case there's always the person, what? But with a cross product, with any cross product, you have a direction for the answer, and you find that direction using the right-hand rule. So using the right-hand rule, the first object, or that variable, the first vector, in your cross product of the two things that are being crossed together, you make your index finger of which hand? The right hand. The second one, you need to orient your hand so you can put your middle finger in that direction. and then the answer is the direction of the thumb. Now, this is the first cross product we've seen in physics. It won't be the last. And so we'll have different things besides just R and F we're using in cross products. So using that right-hand rule to find the direction is always going to be something that we come back to. So, practical example. Let us suppose that I have a wheel and I apply a force on the top that's going that direction. First thing I'm going to need to do is identify the R. When you're summing torques, sometimes there is a clear place your torque is acting. Sometimes there's not. So you need to decide, where am I going to find the torque about? There's always a location you find a torque about. And the torque will be different if you choose a different location. So for the wheel, the obvious place is to find the torque about the center. And so I'm going to do that. How do I define then what the direction is for my R vector in the cross product? Goes from where to where? Okay, from the place I'm summing about to where the force applies. So I'm summing about the center and the force applies above it. So that's my R vector. So now I take my right hand, put my index finger so it's pointing up, because I have my vector pointing up there for R. And then I keep the index finger pointing up and orient my hand so I can make my middle finger point the direction of the force. And then my thumb points the direction of the torque. So the torque in this case would be coming out. Yes, go ahead.
So how do you find the direction of the radius?
The radius is always from the place you're finding the torque about to where the force acts. So now let's take another variation on this just to make sure that we have things figured out. I will make a force that goes like this and acts right there. Somehow, magically, it's acting there on the wheel. So what's the first question I had to ask myself? Okay, where am I finding the torque about? That's what you meant, right? Yeah, where am I finding the torque about? And so let's assume it's the center of the wheel again. And so then where's my R vector form or point if I'm going from the center of the wheel? From the center of the wheel to where the force acts. So there's my R vector. Now these aren't perpendicular anymore. They're reasonably close, but they're not perpendicular. This angle here would be my theta between the two. How do I find the direction for the torque now? Turn this way so I can do it the same as you. Index finger needs to go up that direction, and I need to orient my hand so my middle finger can point the direction of the force, and now my thumb is going into the screen. Now, by convention, into the screen we would call negative, and out of the screen we would call positive. But your thumb is pointing in actual direction. So if you're doing three-dimensional, your thumb gives you the direction in 3 dimensions. Yes, Diksha?
So on that R right there, is it just because you're finding whatever, the X component or whatever?
Not the X component, because I was finding the torques about this point, then my R points that direction. Okay, coming back to my highlight things for reviewing. We've got the conditions of equilibrium already covered, the right-hand rule. Need to be able to apply these conditions to solve an equilibrium problem. Well, I'm going to do that in just a moment. And finally, know the conditions for stable, unstable, and neutral equilibrium. Basics. What does it mean for something to be in stable equilibrium? If you displace it, it comes back. So I'm standing here, got my feet set apart. If Chad were to come and give me a shove, I could move, but I would come back. Unless he pushed me too hard, right? If he pushes me too hard, then I would go to unstable and fall away. So I'm stable for a small push, not so stable for a big push. An easy way to understand this is to think about potential energy. If I'm standing here with my legs apart and Chad pushes me to the side, as I go to the side, I'm actually going to have my center mass go up. And so I was going to higher potential energy. Everything wants to go to lower potential energy, so I naturally fall back down to where I started. Now, if I'd had my feet right together and he pushed me, my center mass would have started falling down, and I would have just kept going. So that's why a broader base gives you better balance, because it's going to make your center mass have to go up if you tip. And so a stable equilibrium is going to be something where you're in a potential energy minimum. You displace and the potential energy is going to go up. Unstable equilibrium, you're a potential energy maximum. You displace and the potential energy is going to go down. And then it'll just keep going to lower potential energy. And then finally we have the neutral equilibrium. If I'm sitting here in my chair with the wheels, I'm sitting here right now motionless. Chad comes and pushes me, or I kick. Now I just move at constant velocity, except for there's friction. I would just be in a new equilibrium, a new velocity, but constant, so equilibrium. A neutral equilibrium will just form a new equilibrium if you displace it. And in that case, your potential energy didn't change with the displacement. Okay, let's go to a problem. So this is a problem I gave on a test once. NFL rules specify that football goalposts are 18.5 feet apart. The crossbar is 10 feet off the ground. The goalposts are supported by a single standard gooseneck, that's this thing here, that places posts 2 yards in front of the single support. The single standard, this thing here, is buried 53 inches below ground. Those are all, the rules specify at least 53 inches. You can bury it more. Now this comes from practical experience when I was in graduate school. After the Cougs beat the Huskies in the Apple Cup, all the fans, students, rush the field, climb the goalposts, break them off. One year they carried the goalposts down to a bar and then went in the bar to celebrate. So a lot of work was done to strengthen them. If you were to watch the Wazoo versus Stanford game Saturday night, you would have seen that they now have a double standard to make it stronger so the students can't break them off anymore. So the question here is, how strong would the support have to be at the bottom? That is, what horizontal force would it have to keep the goalpost from tipping if I have fan, usually wildly drunk fan, standing right here? It's an equilibrium problem. It says up there it's an equilibrium problem. How do you suppose you would start something like this? Draw, yeah. Even if you're in complete bafflement about the problem. I better start by drawing my figure. Now I have something drawn here already, so I'm just going to add to it a little bit. Green would have been a horrible color. So I'm going to have down below the surface the buried part. And then for forces, I'm going to have a force at the bottom and a force at ground level here and a force down below ground level here. Now, you have to think about this a little bit. What direction would the goalpost fall if that person standing on the goalpost made it fall? It would fall something like this. So I'm going to have my forces create a torque going the opposite direction from the torque that person's making. Which means that I'm going to have the ground make a force like this at ground level and a force like that at the bottom. So that those two make a couple that makes a torque the other direction. So I have, let's call this force ground top and force ground bottom.
Can you do that in other colors? Can't really see.
Yeah, I can.
Like white or something?
Well, the problem with white is it's only going to show up on the green. My easy... Orange is not one of my simple colors. My colors are green, magenta, white, blue, red, and black. Yeah, I'll do like somebody said, just draw a new picture. So my new picture. Okay, that pretty much replicates what I had before. Now, there are a lot of dimensional things going on here. What do I care about if I want to find what's going on here? So let's, before I finish working on my picture, let's talk about our concept. What's the concept here? It's in equilibrium. So some of the torques has to equal 0 and some of the forces has to be 0. And so I'm just going to find torques about, it specifically asked me to find force of the ground at the bottom. So if I want to find the force of the ground at the bottom necessary to counter the torque of this person, note that I didn't give you the mass of the goalpost or center mass of the goalpost or anything like that. So we're going to treat the goalposts as if they have no mass. Truth is, you have to have some mass of the goalpost and you have to have some forces to hold up the goalpost. And we're looking at the additional forces necessary for that person to be countered. So I'm going to want to find this force, and I believe I told you the mass of that person. Where should I sum the torques to make this as simple as possible? And I always just put a label there. A. Some torques about A. So force ground top makes no torque. G is for bottom. It's the bottom of the post. The T is at ground level, the top of the ground. T for top of the ground. So that's what I'm going to do. Now, there are more things I need to do now that I've set that forward. Specifically, two things. The first one is more obvious than the second. What's the first thing you think I should do, Anne? Yes, find the force of the person. Thank you. Force of the person is equal to the mass of the person times G, and the mass of the person was given in the problem. We had mass of the person equals, I think it was 95.0, wasn't it? Yeah. 95.0 kilograms. Now that was the more obvious thing. Oh, Reagan, what's the less obvious thing that I need to do with my figure?
I'm not good at figures.
Anybody see what the other thing is I need?
The mass of the goalpost?
Yeah, I need to find what the R is. I need to find, and I'm going to just find components. I'm going to have a vertical distance and a horizontal distance, and I'm going to find the vertical and horizontal distances. So vertical distance is easy. Well, actually, it's not really easy. It also doesn't matter. It's the key. The vertical distance, let's suppose the person's mass is right at the hinge of the goalpost. So their vertical distance above the ground is 10 feet. Horizontal distance, I'm going to draw a picture for that. I have the person's out here at the end of the goalpost. It said the goalposts are 18.5 feet apart. So this is half of 18.5, 9.25. And it said that it's 2 yards or 6 feet from the standard to the crossbar. So this is horizontal distance. This is a top view. And so looking from the top, I have the post sticking straight out toward you at this point with the person standing on it. and I have another one coming out here, the crossbar going there, another one standing up, and then this here is going down. Yes, Austin.
Where do you get the 6 feet from?
I get the 6 feet from 2 yards. A yard, 3 feet. 2 times 3, 6. It said the gooseneck is made so that the standard is 2 yards behind the goalpost, the crossbar.
Oh.
Right. This part right here. Okay.
Are we ignoring the center of gravity of this thing?
We're ignoring the mass of it, yes. We're ignoring the mass of this to simplify the problem. So now I've got my distances. What is my... Okay, here's the vertical part of R is 10 feet. What is the horizontal part of R based on this picture? Yeah. So there I have my horizontal R, and here I have my vertical component of R. The reason I did those separately was because torque is equal to R cross F. And what direction is the force of the person? It's vertical. When we do a cross product, as we were told earlier, we're multiplying the perpendicular parts. So if I have a vertical force, only the horizontal radius matters. The vertical radius just doesn't matter. Hence, it didn't matter if the person was sitting on the crossbar, standing up, it's going to be the same torque. And so I do the sum of the torques about A is equal to, in terms of signs, my radius is pointing, I'm going to change color here. My radius is pointing that direction. The force is down. And so the direction of the torque would be, point my fingers in the direction of the radius, turn for you, so it'd be something like this. Then the direction of the force down. And my torque created by that person is in the direction going, okay, that's an impossible picture for me to draw. But it's going back through the crossbars. So I have that torque, and then I'm going to have the torque caused by the base. What direction is that force of ground due to the base? Vertical or horizontal? Horizontal. So since that's horizontal, I'm going to care about the vertical distance. Well, we were given that this distance here was 53 inches, which would be, let's see, 4 feet would be 48. 4 5/12 feet. So now when I do my torques, I'm going to have, and that would be going the opposite direction. I have to choose one of them as positive, since the one for the person was going generally into the screen. That's going to be the one I put as negative. So I'll have the 4 5/12 feet multiplied by force ground B minus the RH times the force person. And that's equal to 0 because it's in equilibrium. Well, at this point, I can just solve this. Force ground B is equal to RH force P over my 4 5/12 feet. I would have to now get a number from just doing that square root. Let's get, does somebody want to calculate that for me? Give me how many feet that is.
11.03. 11 feet.
Okay, 11.03 feet. Then divide that by 53.48, or not 53.48, by 4 5/12.
Well, that's just the R.
Yes, right. And so divide that by 4 5/12 now. See, it's a little bit more than 2, like 2.5 or so. Five-twelths, I don't know what 5/12 is, sadly.
.50.
Really? Okay. Well, that means that the force the ground has to provide is 2.5 times the weight of the person to keep it from falling over. A standard type equilibrium problem. We simplified it, as Chad pointed out, by saying we're not worried about the mass of the goalposts. The mass of the goalposts are going to probably require bigger force than that person does. But if a person has 95 kilograms, that's a person that weighs somewhere over 200 pounds. You've got somewhere in the ballpark of 500 pounds that are necessary at the bottom to keep that thing from tipping. I now only have 3 minutes left. I had 2 problems for this chapter. Rotational dynamics. Rotational dynamics is using the same ideas that you used before in dynamics, but using the rotational counterparts. So you now have to know angular momentum, you have to know torque, you have to know the rotational inertia. Before we just learned inertia, otherwise known as, what's the other name for inertia? Mass. And the rotational kinetic energy. So you need to be familiar with those. And then you have that rotational equivalent of Newton's second law. We used it on the last problem, we used it somewhere here. The torque net is equal to I alpha is equal to, actually maybe we didn't, is equal to change in angular momentum divided by change in time. So you should be able to use that. You should be able to explain why, for instance, when you lean left on a bicycle, it makes the bicycle tire rotate so that you turn. Why you don't just lean left and fall down onto your left when you lean left. And that's explained with this equation. And then be able to solve rotational dynamics problems using either the work energy method or forces and torques. Now, I don't have time to actually solve these problems, but the first of my 2 problems was one from the textbook. I actually had this queued up to solve over a week ago in class, but we ran out of time. And given that we only have 1 minute left, we run out of time again. The other problem, I think it's more instructional to at least look at the other problem. Question, Ryan?
Well, I was just going to ask, Chapter 10 seems like the least intuitive of all of them. I was wondering if maybe you could do a YouTube video over like that problem.
Yeah, I can do that. Although, see, to my brain, it's the most intuitive because we've already done all of these things. But if you don't see that you've already done them, then it's not.
Yeah.
So yeah, I can do that. I can just do the solutions to all these problems and put them there. Okay, yeah. Thing to point out in this last problem. A yo-yo, you can treat as a solid cylinder. Solid cylinder has I equals 1/2 m radius squared. And when you initially drop it, the string is all rolled up so that the radius for the string rolled up, its unrolling, is about 9/10 of the radius of the entire yo-yo typically. And then when it gets to the bottom, of course, the string is unrolled and it's more like 1/5 of the radius. And so my question was, how do you find the acceleration of a yo-yo? You let go of the yo-yo, if you didn't have any string tied to it, it would just fall with the acceleration of g. But because you have that string, and there's a tension in the string, here's my yo-yo, here's the string with its force of tension pulling up, force of gravity down. If I do the sum of the forces in my vertical direction, its force of tension minus force of gravity equals mg. So, or not mg, ma. So the acceleration is not going to be g, it's going to be less than g. And the question is, how do I find that? Well, this is one dynamic equation, but it's not the only dynamic equation. The other one I'm going to use is sum of the torques equals I alpha. So I have a torque, and I'll do this about the center. So if I do this about the center of mass, I have a torque caused by that force of tension. Using my right-hand rule, that's a negative torque. I have negative, and I'll call this radius of the string, times the force of tension. And if I'm summing about this point, I'd have, actually, technically, plus 0 times the force of gravity is equal to I alpha. Now I have two equations, and my unknowns are now 3. Alpha, acceleration, and force of tension. I need one more equation because you have to have the same number of equations as you have variables. And the last one comes from the relationship between tangential acceleration and angular acceleration. The speed at which the center mass is dropping would be the same as the speed at which the edge is rotating compared to the center. And likewise, the acceleration for the center is the same as the acceleration of the string leaving the edge. And that allows us to make a relationship that the linear acceleration is equal to the tangential, if you prefer, but I'm not going to put that there. The linear acceleration is equal to the angular acceleration multiplied by the radius of the string, because that's where the string is unwrapping. And so that gives us our third equation. 3 equations, 3 unknowns. That's this equation, and this equation. I would solve the top one for force tension, the bottom one for alpha, put those 2 in, find the acceleration into the center one. So that's an example of using forces and torques. Newton's second law is what we would have done before to solve a problem. Okay, I'm 3 minutes over time. Sorry about that. I will make some YouTube videos. I'll put them in the tutorials folder there on the YouTube videos.